Hello and welcome to Leetcodes. Welcome to an exploration of a fascinating problem from Leetcode, problem number 1937. Today, we'll be tackling the challenge of maximizing the number of points with cost in a grid. Imagine you're given a grid of numbers. Your mission is simple yet tricky. Navigate this grid wisely. From each row, you must choose a number. But be careful. Moving too far horizontally will cost you points. Your goal is to maximize your total score. Let's break it down with a concrete example. Here's a 3x3 grid. Each cell contains a number. The challenge is to pick one number from each row. As you pick a number from each row, you'll notice that every row represents a set of choices. But these choices are connected across rows. Here are two possible paths you could take. The first path starts from the top right, moves to the middle, and then to the bottom left. Another path might seem straightforward but could be less optimal. The key is to avoid incurring too many penalties from horizontal moves. So, how do you find the path that gives you the maximum score? Your final score is the sum of the numbers you've chosen, minus any penalties for the horizontal distance you've moved. The strategy lies in balancing the reward of each choice against its cost. Now, let's dive deeper into how we can solve this problem effectively and find that optimal path. Let's dive into a classic problem: maximizing points in a grid. This is a common type of challenge that tests both logic and strategy. Imagine you have a grid of numbers. Each number represents potential points you can collect. Here's an example grid with values ranging from 1 to 9. Your task is to navigate this grid wisely. The goal is simple: collect as many points as possible. But there are rules. 1. You must choose one number from each row. 2. You start with 0 points. 3. As you make your choices, add each selected number to your score. However, horizontal moves come with a cost. Let's walk through an example path. Starting in the middle of the first row, then moving to the rightmost column in the second row, and finally to the leftmost column in the third row. In this path, you collect 2, 6, and 7 points. That's a total of 15 points. But you also incur a cost for moving horizontally across the grid. The cost here is 3 points, making your final score 12. Now, your challenge is to find the path that gives you the maximum final score. Can you solve it? Before we tackle this problem, let's review the constraints and see what we're up against. Here are the constraints you need to keep in mind while solving this problem. The grid has m rows and n columns. Both can be as large as 10 to the power of 5, meaning the grid could have up to 10 million elements. Each value in the grid is between 0 and 10 to the power of 5, so we're dealing with large numbers and a massive grid. In simpler terms, this problem involves a large grid with big numbers. We need an efficient algorithm to handle these extreme cases effectively. Now that we understand the problem and its constraints, let's start working on the solution. Let's start with example 1. Our input is a 3x3 matrix of points. 1, 2, 3, 1, 5, 1, 3, 1, 1. Here's our matrix visualized. Each cell represents a point value. Now, we need to select one cell from each row to maximize our total points. Watch as we highlight the optimal selections. We choose the cell with value 3 from the first row, the cell with value 5 from the second row, and the cell with value 3 from the third row. Let's calculate our total points. We sum up the selected values, 3 plus 5 plus 3, which equals 11. But wait, we need to subtract the number of rows minus 1, which is 2. So our final score is 11 minus 2 is equal to 9 points. Great! Now let's move on to example 2 for a slightly different scenario. In example 2, our input is a 3x2 matrix. 1, 5, 2, 3, 4, 2. Here's our new matrix visualized. Notice it has fewer columns this time. Again, we'll select one cell from each row to maximize our total points. Let's highlight the optimal selections. We choose the cell with value 5 from the first row, the cell with value 3 from the second row, and the cell with value 4 from the third row. Now, Let's calculate our total points. We sum up the selected values. 5 plus 3 plus 4, which equals 12. Remember to subtract the number of rows minus 1, which is 1. So our final score is 12 minus 1 is equal to 11 points. Imagine we have two strings, a source and a target. Our goal is to transform the source into the target using a set of rules, each with an associated cost. The challenge? We need to do this with minimal overall cost. Let's look at an example to make this clearer. Say our source string is ABCD, and our target is A, C, B, E. We have a set of rules for changing characters, each with its own cost. For instance, changing B to C costs 5, C to E costs 1, and so on. Now, you might be tempted to just apply these rules directly, change B to C, then C to E, and so forth. But hold on. This brute force approach could lead to a solution, sure, but it might not be the most cost-effective one. Instead of brute force, we need to think smarter. This is where dynamic programming comes in handy. It allows us to build up our solution by solving smaller subproblems first. We'll calculate the minimum cost for each step, ensuring we always choose the most economical way to transform our string. Now, let's shift gears and look at how dynamic programming works in practice. To introduce this concept, let's start with a simpler problem. Climbing stairs. Imagine you can take either 1 or 2 steps at a time. How many ways are there to reach the top? We can solve this using a dynamic programming table. In this case, dpi represents the number of ways to reach step I. The key relationship here is that dpi equals dpi minus 1 plus dpi minus 2. This is because you can reach step I either from step I minus 1, taking 1 step, or from step I minus 2, taking 2 steps. Now, let's apply a similar approach to our string transformation problem. Instead of steps, we're dealing with characters in a string. Our goal is to transform one string into another with minimum cost. We'll use a dp array where dp j represents the minimum cost to transform the first I characters of the source string into the first j characters of the target string. Let's break down how we fill this dp table. First, we initialize dp0 to 0, because transforming an empty string to an empty string costs nothing. Then, we fill the first row and first column based on our transformation rules. For each cell dp j, we calculate the minimum cost by considering all possible transformations that can convert the ith character of the source into the jth character of the target. We always choose the option with the lowest cost. By following this process, we build up our solution step by step, ensuring we always have the minimum cost for each transformation. This dynamic programming approach allows us to find the optimal solution efficiently. We start with a 3 by 3 matrix. Each cell contains a value, and our goal is to select one cell from each row to maximize our total points. To solve this efficiently, we'll use dynamic programming. This approach allows us to break down the problem into smaller, manageable parts. Let's introduce our dp array. Initially, it's filled with zeros, but we'll update it as we process each row of the matrix. Now, let's look at the first row of our matrix. We'll use this to update our dp array. As we process the row, we calculate 2 important values: the left-to-right maximum and the right-to-left maximum. The left-to-right maximum helps us keep track of the highest value we've seen so far as we move from left to right. For this row, it's 3. The right-to-left maximum does the same, but from right to left. In this case, it's also 3. By calculating these maximums, we're optimizing our choice for this row. This information will be crucial for our final decision. Let's move on to the second row and repeat the process. Notice how our dp array updates with new values. For this row, our left-to-right maximum is 6, while our right-to-left maximum is also 6. These values help us make the best choice for this row. Finally, let's process the third row. We follow the same steps, updating our dp array and calculating our maximums. For the last row, both our left-to-right and right-to-left maximums are 9. This completes our dp array updates. By pre-processing these left and right maximums for each row, we've optimized our dynamic programming solution. This approach allows us to solve the problem in O of m times n, time complexity, where m is the number of rows and n is the number of columns. What's more, we've managed to keep our space complexity at O of n, which is the size of our DP array. This makes our solution not only fast but also memory efficient. Here we have our Java solution. Don't worry if you're not familiar with Java. We'll break it down step by step. This code efficiently solves our problem using dynamic programming. Let's start with step 1, initializing the DP array. We begin by copying the first row of our input matrix into our DP array. This gives us our starting point for calculations. Moving on to step 2, we process each subsequent row in the matrix. This is where the magic of dynamic programming happens, as we build our solution row by row. In step 3, we update our DP array from left to right. We keep track of the maximum value we can achieve as we move across the row, considering the points from the current cell and the best path from the previous row. Step 4 is similar, but we update from right to left. This two-way pass ensures we consider all possible paths to each cell, guaranteeing we find the optimal solution. Finally, in step 5, we find the maximum value in our DP array. This gives us the highest possible score we can achieve by selecting one cell from each row. Now that we understand how the code works, let's analyze its efficiency. We'll look at both time and space complexity. First, let's consider the time complexity. Our algorithm runs in O of m times n time, where m is the number of rows and n is the number of columns in our input matrix. Why? Because for each of the m rows, we perform n operations to update our DP array. We process every cell exactly once, resulting in m times n total operations. Now for the space complexity. Interestingly, despite working with a 2D matrix, our algorithm only uses O of n space. We achieve this by only keeping track of 2 rows at a time, the current row we're processing and the previous row's results. This smart use of space makes our algorithm not just fast, but also memory efficient. Let's start coding our solution. We start by figuring out the size of our grid. It's like setting up a game board, where m is the number of rows and n is the number of columns. Next, we create an array called DP. Think of this as our scoreboard. It'll keep track of the best possible scores for each column as we go along. To kick things off, we fill DP with the points from the first row. It's our starting point, if you will. Now, here's where it gets interesting. We're going to work our way through each row, starting from the second one. For each row, we're essentially asking, what's the best score we can get here? We create a new array called newDP for each row. It's like a fresh worksheet where we'll crunch the numbers. Here's the clever part. We make 2 passes through each row. First, we go left to right. We keep a running tally of the best score we could bring with us from the left. That's our left max. As we move right, we update left max and calculate new scores. We're considering both the points in the current cell and the best score we could have brought from the left. After we've gone all the way right, we start again from the right side. This time, we're thinking, what if we came from the right instead? That's our right max. We go left, updating right max and recalculating our scores. We're comparing what we got from our left to right pass with what we could get coming from the right. Once we've made both passes, our new DP array holds the best possible scores for this row. We update DP with these new values and move on to the next row. After we've worked through all the rows, our DP array holds the best possible scores for reaching each column in the last row. The final step is simple. We find the highest score in DP. That's our maximum points. Let's submit it to Leetcode and see how it performs. Great news! Our solution has been accepted. Here is the final optimal solution once again with detailed inline comments. Imagine you're playing a game on a grid of numbers, and you're trying to find the highest score you can get. Here's how it works. We start at the top row of the grid. We write down those numbers as our starting scores. Then, for each row after that, we do something clever. We look at it twice. First, we go from left to right. We're thinking, what's the best score I could have if I came from the left? Then we go from right to left, asking, what if I came from the right instead? As we move, we have to pay a small price. It's like each step costs us a point. But we're always trying to keep our score as high as possible. After looking both ways, we choose the better score for each spot in that row. We keep doing this for every row, always updating our best scores so far. When we've gone through all the rows, we look at our final set of best scores and pick the highest one. That's it. We've found the highest score possible by considering all the smart ways we could move through the grid. The tricky part is that we're not actually moving through the grid, we're just figuring out what the best move would be for each spot. It's like planning the perfect path without actually walking it. This method is super efficient because we only look at each number once, but we still figure out the best possible score. Pretty neat. Huh? Thank you for watching this explanation of the maximum number of points with cost problem. Happy coding!